Okay, so hello everyone. Welcome to the Physics 1 online tutorial. My name is Kevin. I am a master's student at the University of Ontario Institute of Technology. I'm a recent undergrad. I took physics also at University of Ontario Institute of Technology. So it seems right for me to be doing these tutorials for Physics 1. Okay, let's get started. So this is Physics 1. Tutorial 1. And today I'm going to be talking about the basic units for when we want to describe motion, classical motion that is, and then I'll talk briefly about a number of significant figures, and then I'll talk about the 4 steps to problem solving and the steps to make a really good pictorial representation of your situation or whatever problem that you're trying to solve. And then I'll go over the 1D motion with constant acceleration, otherwise known as the kinematic equations. Okay, so firstly I'll discuss SI units. So when we're describing motion, we always have a body of some mass m, and it'll be moving a certain distance. So let's say he's at x1 to begin with, and then mass m is at some distance x2 to end with, and he went from position x1 to x2 in a certain amount of time. So the velocity to go from x1 to 2 would be x2 minus x1 over the time that it took him to get there. Okay, so if we wanted to write momentum or something for this body, then we would need the mass. And the units that we need the mass to be is in kilograms. So these are the units that we want to use when we want to talk about the mass of a body. And then the distance, or x2 minus x1, will be represented in meters. And the time that it takes for this body to go from x1 to x2 will be in seconds. Okay. So now that we've defined all of our values, then we get, if we were to work this out, we get some value here for the distance and some value for the time, but our units will be in meters per second. Because we have time in the bottom, position on the top, we have to get meters per second for our velocity. Okay, so now that we know the base units for our systems, I'll talk a little bit about sig figs. So whenever we have a problem, let's say x1 equals 102.2 meters, which would be 4 sig figs, and then x2 is maybe equals 1.2 meters, so this would be 2 sig figs, and the time it took is maybe 3.04 seconds. So this would be 3 sig figs. When we compute the velocity here, so v12, so we get 1.2 meters minus 102.2 meters over 3.04 seconds equals some value. I'll call it v bar in meters per second. But then when we actually look at this, actually I'll compute this. So we have 102, so we'll have 1.2 minus 102.2, so we get negative 101 5.0 meters for 3.04 seconds. But now we have to decide how many sig figs that we want to keep. So when we look up here, we have 4 sig figs here, 2 here, and 3 here. And our answer will always want to be in the fewest significant figures given. So since this is the lowest here, we want to represent our answer here. We'll do this as well. 101 divided by 3.04. And we'll want to represent it in 2 sig figs. So we only have 33 meters per second. So this would be the correct answer here, since the lowest number of sig figs in our problem was 2. Okay, so that's significant figures. And now we want to look at 4 steps to problem solving. Okay, so when we approach any physics problem, we really want to start off drawing pictures. And this will help us model to number 1 and 2, which is visualize. So the first thing that I do with any physics problem is always try and draw a picture, try and imagine what's really going on, what's the underlying physics that's happening in your situation, in your picture. So then we want to solve the system after we visualize it and wrote down whatever equations that we need to solve the system. And then we want to assess. So after we've answered the problem, is this a reasonable answer? Do the units match up? Is it a reasonable answer? Is it insanely big? Is it insanely small? If we have any physical intuition to the problem, or does it make sense physically? Okay, so that's the 4 steps of the problem solving. So if we want to drawing pictures, so what are the steps for drawing pictures that will help us solve these problems? So we want to draw a motion diagram or diagrams. And then once we've done that, we want to establish our coordinate system so we know what's negative, what's traveling in which direction, etc. So we want to establish our coordinate system. 3, we then want to sketch the situation. So try and you want to sketch it out so it becomes a model which you can visualize and you can get some intuitive information about. Or you want to define symbols. So what variables will be representing which in your diagram? 5. We want to list the knowns. So what variables will help us solve the problem? And then 6, we want to define our unknown. Or what do we want to solve for in our problem? Okay. So that's the best way to draw pictures because we can visualize it, we know what we have, we know what we want, and this allows us to effectively solve the problem. Okay, so for 1D motion, let's say in the x direction, maybe I'll go down here. With constant acceleration. So we have 1D motion with constant acceleration. So we get the following equations. So the v final, let's say everything's just x here, equals v initial plus a times delta t. So this is the exact same thing as what I wrote above for the x position, where we can say the acceleration equals what was the v final minus v initial over delta t. So if you're traveling at one speed finally, and you're traveling at some speed initially, and you take some time to go from the initial speed to the final speed, then that just equals the acceleration. That's the acceleration in the x direction. So that's one. So another equation, so we can have x final equals where you were initially, xi, plus the initial speed times delta t, plus 1/2 a delta t squared. Because really, if we want to use x final, and we want to include the velocity and the acceleration, then we need the units to work. So if we take velocity, which is in meters per second, and multiply it by seconds, then this will be left in meters. And the acceleration, which is meters per second squared, multiply that by seconds squared, we just get meters once again. Okay, so that's another equation that we can use. The last equation here, if we take v final squared, this equals v initial squared plus 2a delta x. So again, if we're solving for the velocity squared, this will be meters squared per second squared. So this will automatically match up with it. And then, if we don't know what time or anything, but we know the delta x, and since acceleration is in meters per second squared, multiplied by meters, we'll get meters squared per second squared. So all the units match up here, which allows this to be a valid equation. Okay, so if we're talking about 2D motion, where we now have free fall or acceleration due to gravity, then the acceleration in the y direction, which equals ag, which equals g, or a free fall, or negative g because it is in the negative direction, it's an attractive force. This equals 9.80 meters per second squared. So if you use Newtonian mechanics, you will find that the acceleration due to gravity is 9.8 meters per second. And if we're talking about an inclined plane, so if we have some wedge, and we have some theta here, and we have some body here, and we wanted to find, with mass m, we want to find the acceleration in this case. So it'll be a little different because we just want to get the y component. So a in this case equals g sine theta, or whatever this angle is here. So it's now not just theta, or it's not just g in this case because it's not falling straight down, it's actually falling at an angle now. So it's actually g sine theta. Okay, so that is all that I'll be talking about in the first tutorial. And then I'll also be going over problems. So just to recap, here I've talked about the inclined plane, free fall, the kinematic equations here, how we can draw really good pictures so we can actually accurately describe our system and then solve for whatever unknowns we have, sig figs I talked about, and the SI units. Thank you for listening.